Let's continue our afternoon session. Our next speaker is Magnus from Lund University. And we already had a talk about families, so why not having a talk about relatives in K-homology of higher order mathematics? Magnus, the Zoom is yours. Take it away.
Thank you.
The floor is yours, not just.
Thank you. Thank you, the organizers, for giving me the opportunity to talk and a nice conference. I will talk about my work on a generalization of spectral triples. That is my one archive paper, so if you want to see more, you can just find it. It's going to be easy. And to frame one of the results that popped out, I'm going to go through some index things, classic stuff. So we find a nice integer in the wild with the Gauss-Bonnet theorem, which is the Euler characteristic and genus and so on. And this is an index theorem because it's index of the Hodge-Dirac operator. And this can be generalized to a certain theorem for higher dimensions. And of course, we arrive with a lot of work, or kind of at the index theorem, which is quite nice, as I assume you know. And it's quite general. You have any elliptic differential operator in any closed manifold. So it's kind of general like that. But it is 0 in the odd for odd dimensional manifolds. So what's the other side, kind of? I will claim like starts with another nice integer, which is the Winding number, and this is also an index theorem with the Toplitz index theorem. And then we have the Mauvel index formula, which is this thing here, where I have these predictions on the Hardy spaces, and we have some integral on the other side. But this is not really, this is, I mean, here we have a differential operator, but it's very hidden. I mean, it's the d-bar operator inside of these Hardy spaces, and we have restrictions on this domain that it has to be strictly pseudo-convex domain in Cn and stuff. And one thing that popped out from what I'm going to present is a nice generalization. So you have any elliptic differential operator on any manifold with smooth boundary, and you get something kind of similar. So you have the kernel of the maximal domain as the projection and so on. This result is not maybe the interesting part in itself. I mean, to show the last bit kind of uses Atiyah singers and stuff like that, but the methods are, yeah. Oh no, this is a formula that I've come up with, but maybe something similar is known before. I don't know, but the interesting part is this comes from my work on spectral triples or generalizations of them. So let's just talk a bit about spectral triples. So spectral triples for this algebra A, we should think of them. I will do very geometric things with continuous functions almost always. So we have our first we have our dense subspace algebra, which is smooth functions with compact support. Then we have an unbounded self-adjoint operator, which will be some sort of first order operator. If the manifold is closed, it has kind of a nice unique closure, so everything is nice, which will not be the case in the relative. The domain has to respect this dense subalgebra. Commutator has to be bounded, that being said it's a first order operator. And then it has to have some sort of compact resolvent. So we want to generalize this a bit to do higher order. What could we do then? Then we got to change this number 4 to something else. Well, this is a way to do it. So basically, we have the commutator, and then we drag it down m-1 orders using this resolvent thing. This is not originally for me, but yeah. And then if we want to do stuff that is relative, meaning that we want to focus on manifolds with boundary, we're going to have to do a little bit more things. Namely, we have to have, or interesting thing is when you do relative cycles, so then you have continuous functions in the interior and continuous functions including the boundary. And then you gotta change some of these conditions. So you have to have another dense star subalgebra of this ideal J. So I mean, then there is the ideal is the interior and the smooth functions up to the boundary, including the boundaries, then the bigger dense star subalgebra. Where our operator will not be self-adjoint anymore, it will be symmetric. So for differential operators, we think about the minimal extensions and the maximal extension. So the minimal is the closure of compactly supported smooth functions in the interior, and the maximal is the thing that makes sense, the maximum amount of things that make sense in L2 sense. And then we gotta change this domain inclusions a bit so that we can compress the maximal domain into the minimal domain like this. And then actually combining both of these generalizations, you have to do a little bit more. You change this number 5, the compactness a bit, but that's details. So why do we do all this? Because I want to put this in K-homology. So let's just see that it works. And such a higher order relative spectral triple defines a K-cycle with the usual bounded transform, essentially the usual proof using resolvent integrals, but you have to be very careful because it's not symmetric and you have to do some bit back and forth. Just to be clear here, a relative K-homology cycle is kind of the same thing as a just K-homology cycle, but instead you have J's here and an A in the commutator. So the commutator kills off in where we think about this geometric case with manifolds with a boundary. Commutator is still nice even up to the boundary. And here I have a small parenthesis saying that, oh, but this K-homology group of relative J to A is just the same as J. So why do we do this? Well, because say we would have a short exact sequence, J, A, and A mod J, then we can build the boundary map in K-homology. And we want a relative cycle to make it feasible to actually calculate what is the boundary map of such a cycle. You can't just have the K-homology of J. So our spectral triples will give cycles somewhere in here, and the boundary map will map it to something on the boundary data. The interesting, why this is kind of interesting is because if you would have, say, a very nice boundary condition for your differential operator, then one would potentially think it would live all the way up here, where we have stuff including on the boundary. And then mapping it here would give an obstruction to the existence of such stuff. And this is, I mean, this project is inspired from earlier work, of course. And it's, say you have a compact spin C manifold, then you have this canonical class constructed by a Dirac operator. And then Baum-Douglas-Taylor showed that the boundary map of such a Dirac operator is the Dirac operator on the boundary. And I mean, this says quite a lot about the K-homology here, because this K-homology is generated by these operators as a module over the K-theory. And they showed explicitly also that this boundary map works even when you twist this Dirac operators with a bundle. So we want to do the same thing. So let's try to do that for our spectral triples. So the first result, this is not really a big result. It's just the boundary map of this spectral triples. If you assume some part of this operator has closed range, we'll get these two projections. This is just a result taken from book by Higgs and Monroe. So that's not like a huge thing. Here we're talking about no, on my part, yeah, okay. Here it's an odd. I'm talking about even cycle, so that the operator is odd. Yeah, and just to clarify what this right-hand side is, we're using that K1 is just extensions, and then this P is a Toeplitz extension, like this. All right, but what are our examples of higher order relative spectral triples? Well, they are plentiful in that in what we want them to be. So you can have any domain in a manifold. It doesn't have to be compact, doesn't have to have any regularity on the boundary. And then you have any differential operator that is formally self-adjoint. It's hypoelliptic and is elliptic in some sort of calculus. And that can be a variety of things. It doesn't have to be the classical. Of course, it can be the classical. It can be classical with global estimates, so you don't have to have a compact manifold. It can be from the Heisenberg calculus or the Shubin calculus, or yeah, those are the ones I've thought about. But you can just get your spectral triples like this, which is neat. Exactly what is the requirement is specified in the paper, because I don't want to check all the things. So I have a list of these are the requirements of a calculus that I need, and it's not a long list. And yeah, it works very good. So now applying the boundary map to this. Oh, sorry. If we want to have an odd, an even cycle, it doesn't have to go between the same vector bond. It doesn't matter. We just put it across the diagonal, and then we can apply the boundary map, and we get just that it's gonna end up with a prediction on the maximal kernel. Here I've also taken away the minimum extension because it's not dependent on the extension, which is kind of nice to know. Also, if it doesn't depend on lower orders, even no matter which calculus you work with also. This doesn't say that much, and the hope is to, in some nice hyperelliptic cases, work this further. But so far, what I've done is work in the classical, where we have a compact manifold with smooth boundary. So now we have both a compact manifold and the boundary is smooth, and any differential or elliptic differential operators in the classical sense. Then the boundary map can be calculated like this, where we have some vector bundle coming from the Calderon projector, which is a very classical thing, and this vector bundle is very computable. And then we have this fundamental class of the co-sphere bundle of the boundary. Yeah, and what can be said more about this is that this class on the boundary is also point carrier dual to the obstruction found by Atiyah Bot of Shapiro-Lopatinsky elliptic boundary conditions, so very nice boundary conditions. That's not presented in the article, but in future work with my supervisor, Magnus. And yeah, and here you can, it's from this you can just get this Potato-Movell index theorem directly. Yeah, I think that was what I meant to say. Thank you.
Tack.